In this video, we are going to look into some details based on Bayes estimation. This is one of the most important concepts that people would like to explore. Now, the performance measure J Bayes is also otherwise known as a yardstick by which we check the optimality of the Bayes estimate. Now, what is this for checking optimality? The Bayes estimate is the expected value of a cost function. That is how this goes about. So, let us now start the performance measure. J Bayes, or in general, it is also called as a yardstick by which we check optimality of the Bayes estimate is the expected value of a cost function. Alright, in general denoted as C of dot. Okay, this is a function of the error. This is a function of the error or difference between the true value and the estimated value. It is denoted by J Bayes. You have the symbol over here, which is expectation of, that is the mean C of epsilon, the cost function of epsilon, where this epsilon is nothing but x minus x cap, that is the difference between the true value as well as the estimated value. Now we may generate this value of x cap, we may consider x cap. So let x cap be equal to some function, let us say g of z. Okay, so if we say x cap is equal to some function g of z, then I may go on to use J Bayes to minimize the choices of epsilon. How is this done? This is done by using J Bayes C of epsilon, which are squared error, absolute error and uniform error. These are the three choices which we use. We denote it as CMS of epsilon, that is mean square error, which is represented as epsilon squared, and then the C absolute value of epsilon, which is represented as mod epsilon, and C uniform error or uniform normalized error, or CUN of epsilon, which will take the value 0 for mod epsilon less than equal to delta, and 1 for mod epsilon greater than delta. This is how we take this. Here what happens is the CMS of epsilon penalizes large errors severely and rewards errors less than 1. The C absolute epsilon treats error on linear basis. Then the last one, and not only treats it on linear basis, the C absolute epsilon does not it does not parrot if absolute value of the error is within the bound of delta, but it penalizes all the errors which are above delta. Okay, in this case we are going in for CUN of epsilon. Now let us look into these three Bayes estimates, that is the mean square, absolute and uniform. Okay, what is this? You have Bayes estimates are nothing but the cost function C of dot. So first we will look into what is a squared error cost. So what is this squared error cost? So if we consider a random variable, let us consider a random variable capital X. In terms of measured random variable, in terms of a measured random variable, let me say capital Z, for the squared cost error function, then g of Z, then a function g of Z for the optimal nonlinear estimate, for the optimal nonlinear estimate of X is obtained as conditional mean of X given Z. That is, I will have my g of Z is expectation of X restricted to cap Z equal to some small z, which is nothing but integral minus infinity to infinity x into p of x restricted to z dx. Okay, here my x tilde, which is my g of z, x tilde, which is nothing but my g of cap z, is taken into consideration to be given by this integral minus infinity to infinity x p of x restricted to z into dx. Now what is this p of x restricted to z? This p of x restricted to z can be written as p of z restricted to x into p of x, the whole thing divided by integral minus infinity to infinity p of z restricted to x into p of x dx. So this is the formula that we will be using in order to find the squared error cost. Next, we move on to the next topic, that is absolute error cost. So to obtain the optimal estimate in terms of z using the absolute error cost, we must take g of z such that you should take g of z such that your JABS, that is absolute error cost, is minimized. This is the criteria. So how do I do this? My J absolute error cost, this is nothing but, this is the expectation E of the cost CABS of epsilon. This is nothing but expectation of modulus of x minus x tilde. So this is nothing but, in other words, E of modulus of x minus x tilde is taken to be g of cap z. So this is x minus g of z. So this will give me my JABS to be a double integral where I will be integrating integral minus infinity to infinity, integral minus infinity to infinity mod x minus g of z, p of x comma z dx into dz. Okay, so here my p of x comma z could be rewritten as p of x restricted to z, p of x restricted to z into p of z. So our idea is to minimize this JBS. So in order to minimize JBS, it is enough to minimize the term inside the brackets for every value of Z. This is true since P of Z is always positive, as is the term in the brackets. Okay, so next we move on to uniform cost. So how do we go about obtaining this value? To obtaining the optimal estimate of x in terms of z for uniform error cost function. So we are considering uniform error cost function. So then g of z is selected so that we select g of z we select g of z so that your JUN is minimized. Here our JUN is given by double integral minus infinity to infinity. We will have CUN of x minus g of z into p of x comma z into dx into dz. So we need to minimize this. So in order to minimize this, what we have to do is we will start proceeding with the term that is inside. So I will have integral minus infinity to infinity. I will rewrite p of x comma z as p of x restricted to z into p of z. Pull the p of z outside, and then I will have integral minus infinity to infinity cun x minus of my g of z into p of x restricted to z into dx, the whole thing into dz. Okay, so whatever is inside this bracket over here, whatever is there over here, let me take it as I of z. If I am to take this as I of z, if I am to take this as I of z, then what happens when I start solving? That is the ultimate question. If I take this as I of z, what happens when we start solving? So let us first, our title here is I of z. So for this I of z, I may rewrite this I of z. I need CUN. So I may rewrite this as 1 minus p of x restricted to z dx within the integral, and consider mod x minus g of z strictly less than delta, and proceed so as to get my output. So as to get my output. Now let us consider I and start evaluation with I. So my I of z in this position is integral minus infinity to infinity cun of x minus g of z into p of x restricted to z into dx. So this is nothing but 1 minus integral p of x restricted to z of dx, where modulus of x minus g of z is strictly less than delta. Now let us keep this in mind, and minimizing I of z for each z is nothing but maximizing the integral on this right hand side. That is, I need to maximize this portion in order to minimize my JUN. So proceeding in this manner, we may be able to obtain this minimal value this minimal value, and a necessary condition for the maximum a posteriori estimate would be given by this partial derivative got by equating it to 0. So proceeding in this manner, I would have my x cap of un of z would be maximum x p of x restricted to z, and this is approximated to x cap of maximum MAP of z. Okay, so here p of z is nothing more than a scalar factor, and so maximizing p of x restricted to z is equivalent to maximizing the numerator p of x restricted to z into p of z in the integral. So this is how we obtain the cost error in case of uniform cost. Thank you.